tried to spread it out some. So if there's people that you would like for us to consider for the spring, please send me an email, send us an email. But right now, this is what we've got a really good list for the fall, and I'm happy with the list. The second thing is course 595A, which is a special topics course. It's really listening to these talks and then summarizing and thinking about how they're useful, what the impact is, that sort of thing. I have posted, there is the first assignment. This is the talk for today. It's due next Thursday, and for those of you that are in that or online with that, we're rolling now. So, and the instructions are online. They're on the D2L. So if you have questions, email me, and I'll go through whatever you need me to go through. All right. So we've got Professor Jones today. He's the John Paul Schaefer Endowed Chair. You'll notice here that what we tried to do is. Professor Brady last year was one of the endowed chairs. We're trying to do a series of our new endowed chairs, so we were excited. And you notice that we've got quite a few here, so we're excited to have them as speakers. So Jason Jones he's in optical physics, the area of ultrafast, nonlinear spectroscopy, the applications of femtosecond frequency combs. He was instrumental in creating the winter school here, which is a huge deal. He's got his PhD from University of New Mexico. And one thing that was really impressive, he was the recipient of the National Science Foundation Career Award as well as the DARPA Young Inventor. Both of those awards are amazing awards to get both. I've never heard of it. So with that, Professor. Thanks.
All right, thanks for the introduction and invitation to talk. All right, good. Yeah, so it's great to be here. Very happy and excited to kick off this year's Colloquium series and get back face-to-face with everyone again in the classrooms and in the lectures. So it's good to be here. And I'm really excited to share with you some of the activities in our group and with our collaborators. And so please stop me as we go if there's any questions or afterwards, come find me. And we have a lot of fun things coming up, I think, and we are looking for some students that want to get in and participate in some of these experiments. Had a really good working relationship with Dr. Mark Phillips in our group. He's a research professor, and he's been helping with a lot of the experiments and guiding a lot of the numerical simulations and analysis that we're doing. Had good collaborations with national labs and local companies, so I want to be sure to thank Dr. Harilel out at Pacific Northwest National Lab and also some colleagues out at AFRL that we collaborate with. In particular, some of you may remember Ricky Gibson. He's out at AFRL now, and we collaborate with him on some experiments. Also, local companies, Optics Law and MP Photonics. So we have a nice collaboration with multiple labs and people and small companies, and good support for some of these experiments. So let me tell you a little bit today about frequency comb spectroscopy and the different experiments we're doing from the XUV to the mid-IR. And I didn't forget the students. I just didn't have enough room on the first slide, right? So I'll point them out as we go along. But this is the team that's really pulling the weight and doing a lot of the work. All right, so what is a frequency comb? I always start off my talks that way. I know there's a lot of new students, so we'll do it one more time. I know if you've heard my talk before, you've been introduced to the frequency combs before. And a lot of people in the college use these. But I like to think of it as the Swiss Army knife, if not of the AMO lab, of our lab. So let me tell you what it is and the different ways in which we use it as a tool in all these experiments. So let's start with a single frequency laser. And if we have a single frequency laser, it goes on infinitely. The spectrum of that's given by the Fourier Transform, and so it'll just be a delta function in frequency space. Right? Now, if we had some fast switch where we could carve out an ultra-short pulse, if this is optical, then that's probably a 5 femtosecond pulse. Then for that single pulse, the Fourier Transform would have the same average frequency, the same carrier frequency, but because of this Fourier Transform relationship, the shorter our pulses, the broader our spectrum is. Okay? But what if we have a pair of pulses? Right? Other pulse comes, it has the same carrier frequency, and it's coherent with this first pulse. What does the spectrum look like now? Right? Well, the pulses are identical, so spectral amplitude is the same in both cases. But there's a time delay t between these two. Right? So from our Fourier transform, we know that that time delay is going to result in a linear phase shift for the second spectrum relative to the first. Right? So if I were to plot the phase of each of these, there would be just linear shift that goes as 1 over that time delay. So what we're going to have is regions of constructive and destructive interference in the frequency domain. So these are spectral interference fringes that you would see from a pair of pulses. Now from a mode-locked laser, we don't use a pair of pulses, we have an infinite pulse train. And it might look something like this. So these are 3 out of an infinite pulse train. And one thing you might notice is that they're not all identical. Right? So if we look more carefully, we have this envelope for each pulse. Now we have that carrier frequency, but this phase between the carrier frequency and the peak of the envelope is different. Okay? And so we call that the carrier envelope offset frequency. And for a mode-locked laser, that can be different from pulse to pulse, this phase shift. And why is that? Well, physically, if we think of a pulse bouncing back and forth in the laser cavity, pulse is going to travel with the group delay of that envelope. Right? But the carrier frequency can, of course, travel with phase delay, and there's no reason those have to be the same. So there can be this slippage from pulse to pulse of the carrier envelope phase. So then, where does that leave us? Well, before 2000, after 2000, this was obvious to everyone, but before 2000, it wasn't so clear, are the pulses really identical? Or even if there were, is there any phase relationship from one pulse to the next? Or from one pulse and 1,000 pulses later? And what does that even mean, a phase relationship? Well, if there's no noise in the system, then the pulses aren't necessarily identical because of that phase slip that I just mentioned, but they can still have a phase relationship. And if we take the Fourier transform then of this, these regions where we had constructive interference now become like delta functions, right? Just like as we illuminate more lines from the grating, we get a higher and higher resolution. So it's the same thing in the time and frequency domain. We have more and more pulses, and these regions of constructive interference become more sharply defined, and they're spaced by exactly the repetition rate, which is just 1 over that time delay between them. So now these are these so-called comb teeth. This changing carrier envelope frequency from one pulse to the next, that's a phase changing in time. Right? So that's the frequency. And so this so-called carrier envelope frequency is just equal to that phase shift from one pulse to the next divided by the time between the pulses. And so if we look at the absolute frequency of all these comb teeth, trace it back down to 0, there's going to be that shift, and that's the carrier envelope offset frequency. Okay? So if we can measure that, that's in the RF domain, and if we can measure the repetition rate of the pulse, it's maybe like 100 megahertz, then in principle we can determine each one of these comb teeth. Right? So these are optical frequencies, right? They're 400 terahertz. These are quantities we can easily measure in the RF domain. Now we have to know this integer m. That tells us which one we're looking at. But if these are spaced by 100 megahertz or gigahertz, that can usually be determined. So, the big impact the frequency comb had, it was originally developed for optical clocks because they wanted to be able to count optical frequencies. And that was very hard to do. It's doable, but it's a huge effort. Now, this directly links optical frequencies to radio frequencies, right? We can count these two radio frequency quantities, the repetition rate, the offset frequency. We can determine all the absolute frequencies. And that's where it has biggest impact initially, is generating a stable comb. And there's a lot more to that, how you detect the offset frequency and things like that. But I'll also point out then, the other thing that happens, they realize, well, if we stabilize these frequencies, we can control these electric field waveforms, right? And now we'll have attosecond timing control because we know the phase of the pulse. Before the year 2000, the phase was relatively random in these pulses and not taken into account in many experiments. So it really opened up this other field of attosecond science. And around that same time, I'm not sure if it was still Bell Labs around 2000 or not. I think it was. I think it was still Bell Labs, right? They came out with this microstructure fiber, right? And this was fantastic timing because now we can send our short pulses into this fiber. There's really high confinement in this, strong cell phase modulation. You can engineer the dispersion of the fiber and generate supercontinuum. And so people started working right away to see, can we take this really nice structure, this comb, and generate a broadband supercontinuum? And you can, if you do it just right. And so now we have this supercontinuum that's perfectly coherent, or at least it's possible to be perfectly coherent. And it's like having hundreds of thousands of individual single frequency lasers. Likewise, the individual pulses have really high peak energies, peak powers, because they're femtosecond pulses. So we can still drive optical nonlinearity. So you get the best of both worlds. You can study nonlinear optics, nonlinear interactions, and you can also do precision measurements with these individual comb teeth. Okay, so that's the tool we use in a lot of these experiments. And again, before 2000, there was a lot of work in trying to utilize these things, but they couldn't measure the offset frequency. Now that's measured, it's opened up a lot of things. So I like to think of it looking more like this, right? We can access any wavelength region we want, and we have this great new tool, this precise tool. Now, to me, it's this easy, but if you ask the students, of course, each one of these blades takes a while to develop. So I want to tell you about 3 experiments, and I won't spend as much time on these 3, but I want to give you the basic idea of them. And one of them is the use of these as an atomic clock, which is what sort of the original development was. I want to talk about development of sources in the mid-IR and introduce some of the spectroscopy we do out there, and then how we can generate these combs into the vacuum ultraviolet and the extreme ultraviolet. And so hopefully that's not too many topics. We're going to introduce those, and then I want to say a bit more detail about what we're doing studying laser-produced plasmas and why those are interesting, and how we're applying this frequency comb to probe and learn more about these laser-produced plasmas, and we're using these in a variety of different experiments. So first we'll talk about the clocks. Right? So this is being led by Seth and Dylan. And as I said, before 2000, we didn't have this link between optical frequencies and radio frequencies. So people knew they could build good clocks out of optical transitions. There was 1 or 2 examples, heroic effort. But for the most part, we didn't know how to count optical frequencies. So since 2000, this field of developing atomic clocks based on optical transitions rather than microwave transitions has really taken off. And there's just been some spectacular gains. So just to review what we mean by an atomic clock. So we start with some local oscillator. So this could be a microwave horn, or it could be a laser. And we're going to interrogate some atomic transition. That's our spectroscopic measurement. And so we're going to find some transition that hopefully is well isolated, it's well defined, doesn't change in time. And here's just a diagram of a resonance of the transition. And we're going to try and find the center, and we're going to lock this local oscillator onto the center of that transition. Right? So that's our clock. We're going to lock it to this transition, and here's our output that will count. So how do we characterize these clocks? Well, we want a narrow transition for the following reason. It's going to define, the frequency drift of the clock. And so one parameter that's used to characterize clocks is the fractional frequency stability. It determines the precision of the clock, and generally, the more precise the clock is, the more accurate you can make it, because it takes a while to see if it's drifting or not. And we can get this expression, this fractional frequency stability, just by looking at this diagram. Right? So the fractional frequency stability is the uncertainty in the clock transition divided by the absolute frequency of the clock. Now, if we look at this expression, that would be this alpha of t, time variations. We can't control the noise floor of the clock. And that's just going to be related then to the line width of the transition, delta nu, capital delta nu. And then how well can we find the center of that? How well can we split that line? Well, it depends on our signal relative to the noise floor. Right? That signal and noise floor is going to define this region of noise in frequency, delta nu. So this fractional frequency instability can just be written as a capital delta nu, the full width half max of the transition, divided by the signal to noise ratio that you can get, and then divided by the frequency of that transition. And if we write that out in time, our signal to noise just drops as 1 over square root of tau. All right, so clocks are, and the fundamental standards are based on microwave transitions, right? This 9 gigahertz transition and the ceasing ground state. But, here's some of the real workhorses of the clocks today, right, that are actually in use. And these are all microwave clocks. And I've plotted as, performance, which is really just the stability of the clock, versus how big is it. right? The size, weight, and power, the swap of the clock. And so this ranges all the way from tiny chip scale CSAT clocks all the way up to a fountain at NIST, right, where they laser cool the cesium atoms and throw them up and down and carefully measure the transition of the cesium hyperfine ground state. The real workhorse is the hydrogen maser. And this gives you about 13 digits that mean something in 1 second. Okay? Now, on all the GPS satellites, there's going to be something like this Rubidium clock. Right? So that's still the backbone of our timing and use of clocks and networks for most places. The real advantage to trying to develop optical clocks is that we're going from 9 gigahertz to 500 terahertz, or 400 terahertz, because our instability will drop very quickly. And so nowadays, these optical clocks are way up here in performance and size. Right? They're at 10 to the minus 18. Some of the best ones. 1 second. But there's a lot of different applications and uses for clocks. And one of the most commonly used is position, navigation, and timing. And a big concern, of course, right now is when there's GPS-denied environments, you want clocks that can help maintain positions and locations and things like that. Coherent radar, we could have coherent optical arrays as well, long baseline interferometry. Because clocks are so accurate now, the ones based on optical transitions, they're also looking at clock-based geodesy. Right? This is the ytterbium clock at NIST, optical atomic clock. And this is just a NASA figure of the gravitational field of the Earth. Right? But they can tell 1 centimeter displacements by looking at how that clock ticks. So the idea is if we can make these portable, these become more useful in real-world applications. So the one that we're trying to look at, there's a lot of effort of replacing this hydrogen maser. The same performance, but in something that can be taken out of the lab and used in the field. And one approach a lot of groups are working on is this 2-photon transition in rubidium. All right. So what would the clock look like? Well, I got the slides right. There we go. So if we take a cell of rubidium atoms, we don't have to laser cool them. We have a CW laser, we find the transition rubidium, and we lock the laser to it. And now we can count that frequency by mixing with the frequency comb. In fact, if the offset frequency of the comb is 0, then we just count the repetition rate, multiply it by the correct integer, and we know the optical transition that it's stabilized to. So why is this a nice transition? Well, this can be very portable. We don't have to laser cool the atoms because we can do a 2-photon spectroscopic measurement that's Doppler free. Right? So the motion of the atoms results in a Doppler shift and it sort of blurs out the line. And so the highest performing clocks always use laser cooling to get rid of the Doppler induced shifts. With a 2-photon transition, you can have the beams coming in opposite directions. You can absorb a photon in one direction and in the opposite direction for the same atom. The Doppler shift gets canceled. And so you can get these really nice, narrow transitions. These are the different hyperfine transitions for this 5s to 5d transition in rubidium. And we detect it in the fluorescence that's emitted. Okay? So there's a lot of groups working on this. This looks like a nice system in the near future. What we're doing, though, is to get rid of that CW laser and use our new tool, the frequency comb. Right? And so we're going to directly probe this 2-photon transition and just have the frequency comb take care of everything for us. And we'll use the output and count that. This spectrum, actually, they just took recently, was with this frequency comb. So this is a direct measurement of the 2-photon transitions with the frequency comb. And sort of a big thing we were able to show this past year was that we can get the same resolution as you'd get with the CW laser. Now, if you think about it, here's the transition we're measuring, and our frequency comb is broadband. It has a lot of individual frequencies, but how do we get a narrow transition as we scan it across this resonance? Well, it's because it's a 2-photon transition. Right? So what we have is one comb tooth here might absorb 2 photons from the same comb tooth. Right? But we can use adjacent comb teeth, and those pairs will also have the same net energy to drive that transition. Right? So if you're looking at a 2-photon transition, you can get the exact same performance with the Modoc laser in terms of the excitation rate and the resolution as you do with the CW laser. So we're looking at that more carefully and looking and studying this 2-photon interaction with the frequency comb for these clock operations. So this is the way it works. I said, we have a pulse coming from this direction, a pulse coming from this direction. And what you always have is the pulse goes along through the cell, and here's the Doppler-free excitation where the pulses overlap. But you always have these other regions where there's a Doppler broadened background. Right? So you'll have your two-photon transition. You'll have this Doppler broadened background where the regions, they don't overlap. You'll have that with the CW case too. With the frequency comb, we have a few tools and tweaks that we can do that you can't do with just a single frequency laser. So we can use the whole spectrum to engineer and change things a little bit. And a group demonstrated this a couple years ago, but one thing is we can shut down or shut off this background. If we can control the spectrum and the phase, we can, for example, get rid of the comb teeth that are directly resonant with it and just use the adjacent pairs. Right? So there's no excitation from the pulses coming from this direction, no excitation from the pulses coming this direction. Only when they're overlapped you get the two-photon excitation, and then the background is gone. And then that can help with things like positioning and stability. But with this very broad spectrum, there's a lot of other things that we're looking at, and we won't go into detail. One is that the rubidium atom, of course, has a lot of different transitions. And so if you're locked to a transition, you want that clock to stay stable for a long time, and you can't always tell if something's shifting. The dominant uncertainty in these is the Stark shift, because it takes a lot of power to make a two-photon transition. So you have, if your intensity changes, the transition changes. So other things that we can look at is, well, we have the spectrum from this one laser to excite another transition over here. Let's excite two different transitions that have a different Stark shift dependence. And now if our power drifts over time, we'll see the difference in those two signals. So we can use the broad spectrum to interrogate multiple transitions. We can also use the broad spectrum for something called Stark shift mitigation. This Stark shift that pushes the transition one direction, it depends on the wavelength of the laser light. And so we could use some of the light at a different wavelength that shifts the transition in the other direction and get that in just the right ratio to get rid of this long-term Stark shift drift problem. So we're looking at that, and Seth's been actually collaborating with our colleagues at AFRL who've been working on sort of the CW laser version of that. We're also collaborating with NP Photonics, funding through DARPA, and trying to fit all this into a 3U-sized rack enclosure. Right? So this is something people are working on right now, and they're going to continue to try and shrink this more and more in the future. So that's been a fun project to work on. Okay, moving on to the mid-IR. Okay. Let's go and look out here and how we generate light out here with these frequency combs. And now we'll move away from clocks, and I want to talk about, really highlight here two different spectroscopic techniques. Right? With the rubidium, we looked at direct excitation. That was really convenient. All the comb teeth could lead to the excitation of the transition. Let's look at how we can do molecular spectroscopy with these combs. Now, it's actually not that hard to get to the mid-infrared. Right? We have this broad, coherent spectrum, so we can do difference frequency generation in nonlinear crystals. A lot of people have been working on that. And so we just take two portions of our broad spectrum, in this case 1030 nanometers, 1560 nanometers. We mix them in piplin, or we also got from our colleagues optically patterned gallium phosphide, and we can generate light out in the mid-IR. So in this case, we're going to 3 to 3.5 microns, and the spectrum shown here. We can also go out to 8, 9, 10 microns with this difference frequency generation in different combs, different laser systems. I want to highlight two different systems. One is based on a collaboration with Jerry Maloney's group and also with Ricky Gibson out at AFRL. And a lot of the work that I'm showing here is done by Robert Rockmore, who some of you might know. I got his PhD in Jerry's group and is out at AFRL now. Now, there's a lot of groups here, several, that work with these vertical external cavity semiconductor lasers. Right? There's some real experts in this department, all the way from microscopic modeling to the modeling of real-world things like the dispersion in the cavity. And they've been working on trying to generate very short pulses from these VCSELs. And I've been working with them a little bit on that. But what I want to point out here is that with these structures, we can generate short pulses, but it's also nice because we can generate pulse durations of 1 to 10 gigahertz. Okay. Now, with the fiber laser and other laser platforms, it's typically around 100 megahertz. Okay. And why is that important? Well, it moves the comb teeth out further away. It makes it easier to identify, and you can get more energy per comb tooth. All right. So we worked together on that to try and show that we could generate frequency comb, and we could translate it out to the mid-IR. And I also forgot to point out that when we take the difference between these comb teeth and these comb teeth is from the same comb, right? So when we take the difference, the offset frequency cancels, right? It's one comb tooth energy minus the other, right? And so this is what we call an offset-free frequency comb. There's no carrier envelope offset frequency. So we did that with the Vexel structure. And what's nice now is that the teeth are far enough apart that we can see the individual comb teeth. Okay? And so we use what's called a VIPA spectrometer to image the individual comb teeth. Now, other groups have done this, but typically what they've had to do is use a filter cavity to push the repetition rate high enough. Okay? And those are cumbersome, and they don't filter out all the comb teeth. So this is an image Robert was able to make. We collaborated with AFRL. Ricky brought out this very nice camera. And so it goes through this VIPA etalon off of a grating, and it's imaged onto the camera. So this is the dispersion direction for the VIPA, and this is the grating. And so you get these rows and rows and rows, I guess columns, of comb teeth. Right? You can see individual frequency comb teeth, which is pretty interesting. Now we can introduce some gas, like methane, strong absorbed at 3.5 microns, and you can literally see the absorption features as the comb teeth are absorbed. Right? So we can get really high resolution spectrum, and it's an absolute measurement. So if we go through, and Robert spent a lot of time getting the algorithm to read this out correctly, this is absolute frequency measurement, and so we can compare it with a high trans simulation, and in black is the measured spectrum of methane, and then that's the simulation. It agrees very nicely. So it's a very nice tool, and we want to continue using these in other experiments, but it makes a nice comb. So this is one way to do spectroscopy. If you can see the comb teeth directly, you just see which ones get absorbed. Right? I think that's just when he released some methane into the closed container. All right. Now, there's another approach to doing spectroscopy with the frequency comb that we'll use from now on for the rest of this talk. And that's called dual comb spectroscopy. And so Ryan, and there's been a lot of help, a lot of people working on this home-built erbium fiber laser systems. And there's 2 erbium fiber laser systems. But Ryan's really been the lead on this, putting all this together. And each one of them, we do difference frequency generation. Okay? Nice and simple in a diagram. Takes a couple years to do. So now we have these 2 combs coming out, about 8 microns, and we overlap them on a beam splitter and look on a photodiode. And we see an interferogram that doesn't look this good. It's just a picture I grabbed somewhere else. But this is the interference between those 2 pulse trains. So these 2 lasers are frequency combs, but they're stabilized together, and they have just slightly different repetition rates, say 400 hertz or something. All right. So let's look at dual comb spectroscopy and see if we can good understanding of what's going on here. And it's analogous to Fourier Transform spectroscopy. Right? So in Fourier Transform spectroscopy, it's been around for a long time. What's nice, you don't need a laser. You don't need a coherent source. Right? You have some broadband light source, and you send it through an interferometer. And one of those arms of the interferometer is moving, and you take the light that's combined and interfere on a photodiode, and you can add some gas cell in that arm. So you have to move this mirror very carefully in a calibrated way. But this is a first-order correlation of the field, so it doesn't matter if that's a laser or a light bulb. It doesn't care. This first-order correlation of the field won't know the difference. Right? If you're familiar with the Wiener-Khinchin theorem, what we're going to see, if we take the Fourier transform of that interferogram, is the power spectrum of the light source. Right? It won't tell us any information about the time structure of it, but it'll give us the power spectrum. And then we'll see the absorption features if we have some gas cell in there. So this is mainly the optical interference. That's exactly what happens in dual comb spectroscopy, right? Except that we just have it come in discrete pulses. When the pulses overlap, we get interference, and then from one pulse to the next, they start to walk away because they have different repetition rates. And so we get the same kind of interferogram. All right. So if we take the Fourier transform, then we measure this in the radio frequency, but there's a scaling factor, so we know exactly how that relates to the optical frequency. So this is very nice. We don't have a long mechanical arm. We have all the precision of the comb. And if we zoom in to a section, we can even see the individual comb teeth. We don't need the camera. We can look at much broader bandwidths, and we have a high resolution, and we can scan very rapidly. Right? So it's a very nice system. If we look here at the spectrum that they took, this is nitrous oxide. Oh, there it is. Yeah, nitrous oxide. Okay. Now, this is in the time domain. So again, this is the interferogram, but it's really zoomed in. So the interferogram is much, much larger. But that's just the optical interference between the pulses. What you can see nice and clear in this particular picture is the re-emission by the molecules, right? That's the free induction decay, the molecular emission at later times. It's very periodic because of the structure of the molecule. And when we take the Fourier transform of this, we do some averaging, apodization first. Then we get this very nice, clear molecular structure that agrees well with the high tran calculations. So dual cone spectroscopy, it doesn't matter if we're in the mid-IR or not. It's a very nice way to use these frequency combs to make precision spectroscopic measurements. All right, so then let's move on and let's look at some applications and a harder problem, which is how can we generate these sources in the vacuum ultraviolet. All right. And so a lot of students have worked on this laser system over the years, and some are on here, but most of this work has been led by Kane, pushing on generating light in the VUV and doing dual cone spectroscopy in the VUV. And John's joined the team now, and he's going to continue hopefully pushing in that direction. Although I didn't have his photo, so sorry. So this actually is a spectra that we've recorded previously. So here's a coherent supercontinuum that we can generate pretty easily. It's very hard to get down here in the vacuum ultraviolet and the extreme vacuum ultraviolet. I know there's different terminology for VUV and XUV. But once you get below 200 nanometers, you get strong absorption from oxygen. Right? So if you're going to be below 190 nanometers, you need to be in vacuum. Not everyone here works at total vacuum, but the absorption length is very, very short. And once you get below 100 nanometers, you're really going beyond sort of the ionization level of most materials, most atoms. So sometimes it's referred to as extreme ultraviolet, down there at 50 nanometers or so. And there's a lot of interesting science to do in that region. And there's not good sources to do precision spectroscopy. Even if you had a single comb down there, it would be hard to do any spectroscopy with it because you don't have a lot of power. And so we want to do dual cone spectroscopy down in the vacuum ultraviolet. And there's a lot of things to look at. One is, I think we'll look at is the charged ions, especially for applications with colleagues looking at, well, for astrophysics applications. And there's molecular species. And there's even this M1 nuclear transition in this thorium isotope that a lot of groups around the world have been looking for. It's supposed to be around 160 nanometers. So that would be another perfect thing for the dual cone VUV system. But let me just tell you a little bit about the system. The way we do is we start with a fiber frequency comb, but we go into an enhancement cavity so that we can build up the pulse energy. And so we come with maybe 50, 30 watts. We can build it up to 5 kilowatts in a 100 femtosecond pulse. Right? So we have a coherent pulse train, so it's still a frequency comb, but now we have high enough pulse energy to ionize the small gas jet that we place in there. Okay? And there's a process we won't get into. It's called high harmonic generation, and it's a nonlinearity, but it's not like the bound nonlinear optics that you hear about. It's extreme nonlinear optics, right? You're actually ionizing, ripping off an electron, and recolliding with the pore. And the end result is that you can get very, very high harmonics generated. And we can do this with the frequency cone now. And so you can see the xenon gas being ionized, and then you can see the XUV beams hitting the sapphire plate. And so we reflect the higher harmonics with the sapphire plate because down at 100 nanometers, the index refraction is different, right? So the main pulse goes through that. It's that Brewster's angle, but some of the higher harmonics get kicked out. And then this is what we can see down to about 60 nanometers in that setup. But for dual cone spectroscopy, we need 2. So this has been a beast of an experiment. And a lot of people put in good time in it. Kane's really been careful to get everything running at once. He's been juggling a lot of balls. And now we have these 2 frequency combs, 2 femtosecond enhancement cavities, and we can combine the beam and look at the interferograms for the fundamental and the third harmonic. Okay? And so we hope to do this same type of dual cone spectroscopy in the VUV and the XUV. And this summer we got our first results, Kane and John pushing on it, and just with the third harmonic, just our initial results at 348 nanometers, but we're able to see these absorption lines in cesium with the third harmonic. And so now we hope to look further and further out into the vacuum ultraviolet. But we're really excited to finally get some absorption spectrum taken with that. All right. Well, that's all I wanted to say on that, because I want to tell you a little bit about some of the work we're doing investigating these laser-produced plasmas, and we have plans for all the tools that we have to study these laser-produced plasmas, because there's just a lot of different applications that we're working on, and people we're collaborating with to explore these. So what are these? Well, this is a chamber where we have some solid sample, and so we use something like 10 nanosecond pulses from a YAG laser, 50 millijoules. So these aren't extreme plasmas. Right? We're generating temperatures at around 1,000, 10,000 Kelvin, and number densities given there. And things are happening on nanoseconds to second time scales. Right? So you have up to about a microsecond a strong plasma. And then you get neutrals that start to form, and then eventually molecules form. And then later, you get cluster formations and things like that. So there's a lot of interesting things happening. It's very complicated because all the different broadening mechanisms, Stark broadening at earlier times, Doppler broadening from the motion and collisions. And then there's also matrix effects and a very congested spectrum if you have a lot of things in that sample. Now, it's interesting for a lot of different reasons. One is just convenient sample preparation. If there's an atomic system or molecular system you want to study, it can be very hard to generate that. If you want to look at iron, you need a very hot oven, or you can use a laser-produced plasma. So it's a convenient way to look at different systems, and that there's just fundamental properties of atomic molecular systems and ions, right? So we've been looking at identifying, every time we do the experiment, we see new transitions that haven't been recorded. We come up with ways of measuring oscillator strengths for a number of transitions that aren't recorded. So there's a lot of just basic fundamental optical properties that you can get, atomic properties that you can get in these experiments. There's also a lot of interest in better understanding the plasma dynamics. I mentioned the time and temperature scales over that. It's also it's a surrogate, and how good is still an open question, for different environments. You have really high temperatures and rapid expansion and cooling. And so there's a lot of people looking at these as a surrogate for studying similar things in nuclear explosions or chemical explosions. How good of a surrogate is it for it is still an open question. Also working with a group, we're hoping we'll be funded, we'll see, on they're studying kilonova. Right? And so people think that a lot of the heavy elements are generated in these rare kilonova events. They were the first ones to identify strontium emitted from one of the supernova. They need a lot more information, and so one way is to use these laser-produced plasmas as a surrogate for that, and to look at a lot of different heavy elements and ions of these heavy elements because they need to identify what they're seeing. So the laboratory-based astrophysics. And then just general optical analysis of solid materials, right? So there's a lot of interest in this. We have a colleague working on, characterizing mine ore. A big application is isotopic analysis. So our colleagues at Pacific Northwest National Lab are very interested in using this to characterize radiological materials. For that, you need really high resolution to see if there's isotopic shifts. Right? There's a lot of information if you can determine the isotopic structure of an element. So those are the applications. Now, laser-produced plasmas have been around a long time, this laser ablation spectroscopy. If you look at the light emitted from it, it's typically referred to as laser-induced breakdown spectroscopy. Right? And it's a very nice, simple system. You just need a spectrometer and a laser to blast something. Right? And that's exactly what the rover is doing. What's doing up on Mars. It has a Lib spectrometer on it. It's analyzing soil and rocks from the Martian surface, looking at the light emitted from it. There's some limitations, of course. It has a limited spectral resolution. It's only as good as your spectrometer. If it's really strong plasma, there's self-absorption, and that gives you distortion on line shapes. And you're looking at the emitted light, so it's hard to get absolute numbers on quantities like the density and things like that. Now, CW laser absorption spectroscopy to probe the plasma works well. You can have a really high resolution. You can look later in time, right? The emitted light only comes at the beginning of the plasma, right? At the first burst, and then it dies off. With absorption spectroscopy, you can look at later times. You can still see what's there and what's happening. You can also look at it at lower temperatures, so then things have cooled down and you have a higher resolution. Right? So you can do much higher resolution analysis doing absorption spectroscopy. And it's a direct measurement, so you can get things like the density with much more accuracy. Right? With the CW laser, there's other limitations, limited scanning range and speeds and things like that. So what we did a few years back was to use this dual comb system to study these laser-produced plasmas in absorption. All right? And so we took some NIST glass that had a small fraction of rubidium in it. And like all AMO people, we love rubidium. We like the D2 line. Everyone uses it. And so it's well identified. It's a strong absorber. So there's rubidium-85 and rubidium-87. And so we expected to see these 4 transitions out of those hyperfine states in those 2 isotopes. So here's the result of a single-shot measurement that we did. And you can see it's very broad now, 780 nanometers to 764 nanometers. And in that glass, we also saw strong lines, D1, D2 lines of potassium. There's that D2 line of rubidium that we're looking for. And when we zoomed in, we could see those 4 transitions for the rubidium. Now, this is just a single shot, and we can get much cleaner spectrum if we average. But we're very happy with that. It proves the point that this is a very powerful tool for looking at and learning more information about these laser-produced plasmas. But in that experiment, we just did it. There's no time resolution, really. So now we want to time resolve the laser-produced plasma, right? Because this is really evolving. You have ions at the beginning, and they're disappearing. Atoms are growing, and molecules. So we really want to see what's going on. And can we do it with the dual-comb system? Now, I said you get an interferogram, right? The optical interference from the 2 pulse trains. But they walk away, and then they come back, of course, right? So the interferogram repeats periodically, right? And it's 1 over the difference of the repetition rate. So this is hundreds of hertz difference in the repetition rates of the 2 lasers. Then that interferogram repeats every few milliseconds. So what we do is a little detailed diagram. We have 2 frequency combs. We frequency double them. So now we're at green. We're on 500 nanometers. This is just a spectral filter. We spec the region we want, and we send it on to a double balanced photodetector. And so it's just our dual comb system in the green, and then this is what we see in the time domain. All right. So if we look at just this first pulse interferogram, we take the Fourier transform, that's our reference. So this particular one was 72, oh no, this is just the reference. So here's our reference spectrum. We have some fringes from some optics in it. But then we fire the ablation laser and generate a plasma. And so we've timed it so that the second interferogram comes some time delay after that. So we record a reference, and then we can quickly record the absorption spectrum at some time delay after that. And then we can just change this time delay. Right? And so from this, we can calculate the transmission and then the absorbance. And so it's really nice to have a really good reference because this happens so quickly, and we can do it over and over on average. And that's the basic idea. Getting the timing right, getting the lasers stable and coherent is the longer story. So this is an example of something that we would see. So in this case, it's an alloy that had iron, neodymium, and gadolinium in it in different amounts. And we averaged it. And then this is just stepping at times from 30 microseconds out to 150 microseconds. Okay. The other part of the problem is figuring out what all this means, what this tells us about the plasma. Right? But we have these really nice sharp lines. And let me point out one thing. Let's see. These 2 lines here persist for a very long time, right, compared to the other ones. You see the same thing here. It's a simpler system. This is just iron. Okay? So there's not as many lines to look at in their colors, so I can point to them. So here's some of the transitions of iron. And we're looking at 3 of them. And these are all excited state transitions between this level, and this level. And how these get populated depends on the excitation temperature of the plasma. So we can also learn a lot about the plasma itself. And this lower transition, that's this green line here. You can see at the earliest times, it's a little shorter, and then it grows because initial times when it's hot, there's more population, and as that population decays back down, these other transitions, the higher transitions, go away first. So that's kind of some of the information you can get just by looking at that. We also wanted to be able to record events for all time delays at 1 shot. And we can still average, but there's a lot of wasted time between those interferograms coming at 2 milliseconds. So we just got a bunch of beam splitters together and made a multiburst pattern. Right? So now we split that 1 interferogram up into about 8 of them. Right? And then it repeats itself a little bit later. This worked very nicely. And again, if we zoom in, there's the free induction decay. This would be the reference. This will probe the plasma. And we take the Fourier transform. Now we can see this. In this case, it's neodymium lines. This is the single shot spectrum that we recorded. And this is the time average spectrum that we recorded. You can see all the same spectral features. Of course, the signal to noise gets better. It's also typical of what we see when we do these experiments. We have so much information. These are all transitions that we know are real. They're dipole-allowed transitions, but they haven't been measured or recorded before. So maybe we should get someone at NIST working on this, right? Because it just can fill up the databases. So these were all new lines we identified when we did that. But the point was to show this multiburst technique and that we can fully characterize all the information from a single shot. That's important if you're looking at, say, an explosion. You can't repeat it 20 times or 100 times. So those are the different modes in which we use it in. Let me tell you then about, just give an example of some of the information we can extract. And again, Kane, a lot of different people have worked on it, and Reagan's probably done the most, leading these efforts in analyzing that, and guided by Mark in the simulations and things. So we can get things like number densities as a function of time, how it changes, excitation temperature of the plasma. We also came up with, Mark led this on, ways to read out the oscillator strengths for all these transitions. Okay? So a lot of good, useful atomic and molecular information for those different applications that I mentioned earlier. Let me just give you an example of what they do here. Here's just a few of the transitions at one particular delay. Okay? And so the experimental data you can barely see because it's overlapped with the fit in the blue lines. So this is for a sample that had gadolinium, neodymium, and iron in a known ratio that we ordered. Okay, so we do a fitting algorithm to all these transitions. This is the residuals. And then we calculate the area underneath the curve for all these different transitions. Now we know what the area, once we get that number, tells us, right? It's related to the absorption coefficient. And so when we measure the area, if we know the oscillator strength and the degeneracy, then we can determine what the number density is for that lower level. And that's what absorption spectroscopy is. You can directly probe the number density. Now, we don't quite yet have the information on the length of the plasma. These are very inhomogeneous. So we call it a column density. Right? So we can measure directly the column densities, and it's state resolved. Each one of these transitions, we know at this point in time, what's the number density there versus here, and how does that change in time. So with that, we can do one example. We can do what's called a Boltzmann analysis. Right? It's very common in LIBS, laser-induced breakdown spectroscopy, and we can calculate this at each time delay. It's interesting. It assumes that there's local thermal equilibrium. Right? That doesn't mean that all the atoms are in thermal equilibrium, but locally they are. Okay? And that's going to be true if these collisional processes dominate over radiative processes. Now, in the end, we know it's a good approximation because our lines are linear. Now, let me show you what those mean. So Boltzmann distribution tells us how these number densities are going to be populated for a given temperature if everything's in local thermal equilibrium. Right? This is the total number density, which we don't get from these measurements. We get the state resolved number density, total number density, and equipartition function. Now, if we move this around and take the natural log of both sides, we can put this equation into this form. Right? And so on our y-axis, we've plotted this natural log of the state number density length over the g factor. But it's equal to now this natural log of something that has the total number density in it minus 1 over k times T, the temperature of the plasma. So that's a long story, but what it tells us is that when we make these plots using all those different molecular transitions, the slope of this tells us the temperature of the plasma at that time. And then this intercept tells us the total number density in the plasma at that time. And you couldn't get that otherwise. That's very useful information to see, just to understand what's going on in these laser plasmas. And it was also interesting to compare now the temperature for neodymium versus gadolinium. Are those going to be the same? There's different equations for the ions, and so we're also going to study that in the future. And so what we see here is the excitation temperature for neodymium and gadolinium as a function of time delay, and they agreed very well. Right? Now, maybe they should, maybe it's obvious. But then we also looked at the number densities. Right? So this is the total number density as a function of time delay for neodymium and gadolinium, and this is their ratio. Now, these are supposed to have the exact same ratio in the two, and so there's a lot of interest in knowing how accurately this would work for telling sample composition. It could be like an optical version of a mass spectrometer, but they don't agree. All right, the ratio is 2 to 5 times off over that time. So it brought up a lot of interesting questions, and I'll just touch on them. First of all, should the excitation temperatures be different? It all depends on this condition of local thermal equilibrium. There's also a lot of spatial inhomogeneity in the plasma. So it's pretty interesting that they actually agreed as well as they do. So that was nice. What about the number densities for the species? Well, there's a lot of questions on elemental fractionation. When we hit this thing, are we going to generate the same number density? Even if it's a different number density in the solid, is it going to be the same when we ablate it and generate a plasma? They could have different molecular formation rates, so does it depend when we look at it? Ionization rates, that could be different. So it brings up a lot of questions that we're looking into. One that we've seen now, of course, is that they can form molecules at different rates, and then those atomic lines disappear. Right? So we started looking for molecules in these laser-reduced plasmas, and in particular oxidation of it. Right? And so again, Ryan is really leading this part of the experiment. Ryland's been joining him, and we have a lot more planned on studying molecules. So we looked at a solid target of cerium, and had a regular background, or even went up to atmosphere, and there was no lines. There's no atomic cerium lines and no cerium oxide lines. Right? So what they did is they had to, of course, scan the surface and get off the oxide on the top, and then they had to go to a lower background pressure and get rid of all the oxygen in the chamber. So we think what's happening is it forms a higher order oxide too quickly, and there's not cerium or cerium oxide. Right? It all goes somewhere else. So once they did that, then they could resolve these nice cerium oxide lines, right? We can see the P, Q, and R branches. It turned out that this was rather difficult to figure everything out. We were hoping to get the molecular vibrational temperature from it, and we still can, but we got a lot of information, agreed well with previous ones, but we have the resolution now to see these molecular band heads at different times and identify everything and really resolve these rotational vibrational transitions of cerium oxide. Let me zoom out and show you the full spectrum at different time delays. So this was the one I just showed you at this last, I think it was this last one at 300 microseconds. And now we see other band heads in this region, and we also see a lot of cerium lines. So we have this mixture of cerium and cerium oxide forming, and now we can see the amounts of each, and we can start studying temperatures and things like that. In this case, we used the cerium atomic lines to do that same analysis so that we can tell what the temperature is as a function of time and then see what the molecules are doing. And this is just the first results from that. Simultaneous comparison of the plasma temperature, the cerium and cerium oxide populations as a function of time delay. So what's next? Well, we want to compare things like this excitation rate versus the vibrational temperatures. So we're going to look at different molecules that form. When do these molecules form versus different temperatures of the environment? The formation of higher order oxides. We have this comb, so we can look at different spectrums at once, and we can see when maybe cerium oxide and then the next higher order oxide forms. And we want to go to higher resolution studies as well. So we're talking with some collaborators on setting up buffer gas cooling. We've also already have some results on some Doppler-free techniques. That'll be important if we want to look at higher resolution studies of ions, which are interesting particularly for these kilonova studies. We also want to look with some colleagues that are looking at molecular ions as potential qubits. So we're going to try and go to some higher resolution techniques as well. And of course, we'll be able to look at a lot of things in the vacuum ultraviolet for the first time because there's no other system that has this type of optical resolution. We want to spatial resolve the plasma and look at the velocity field because these are very complicated in 3 dimensions. People have done that with emission, and we have some ideas on how we can do that in absorption. And that's all I have. Again, I want to thank the students that worked on it and the collaborators over the years. And Caroline helped build a lot of these systems, and she's now with Quantel. And yeah, happy to take any questions. Thanks.